Hello, everyone. Welcome again to PyData Global 2024. I'm Conrad, one of the co-chairs of the conference, and it is my pleasure to introduce Professor Alan Downey, Professor Emeritus at Olin College and Principal Data Scientist at PMC Labs. Alan is also the author of several books, including Think Python, Think Stats, and Probably Overthinking It. He is here with a tutorial on time series analysis with StatsModels. So thank you, Alan. Please take it away.
Thank you. Thanks, Conrad. I appreciate that introduction. And thank you, everybody out there, for joining us. Let me share my screen and we will get things started. So if this is working, you should be seeing my title slide. And there's a URL there that will get you to all of the resources. And this is also in the resources tab on AirMeet, but it is tinyurl.com, DAO24TS, and that'll get you to the landing page. You'll need that in a few minutes when we get to the notebooks, and I'll repeat that when we get there. But if you get a chance to open that page, I'll give you a short introduction. As Conrad said, I'm a professor emeritus at Olin College and now working as a data scientist at PyMC Labs. We do a lot of work with Bayesian statistics and consulting in that field. I am just outside of Boston, and in fact, we are just getting our first snow of the season right now. So it's a big day here. And today, what we're talking about is time series analysis. The idea is usually repeated measurements over time and usually equally spaced measurements. And for this kind of data, all of the general purpose tools that you would use for any kind of data analysis are appropriate. So you can use regression and things like that. But time series are different from other kinds of data. In particular, there tend to be a lot of correlations in the series. So each value is usually correlated with previous values. And there are often periodic patterns. If you're measuring things over days or weeks or months, there are natural patterns and societal patterns that you're going to see in that kind of data. And then the random variation that's imposed on top of all of that sometimes follows distinctive patterns. So there are a lot of specialized methods that are used for time series analysis. And a lot of them are available in StatsModels. So if you are a Python user, a lot of these tools are readily available, and that's what I'm going to show you today. So the topics we'll cover will do seasonal decomposition, which is maybe the most straightforward method for time series analysis. It's a good place to start. And we'll also talk about making predictions. So not just analyzing data, but making forecasts for the future. And then we'll talk about autoregression and ARIMA models, which are based on autoregression. For what we'll do, we'll go what I call bottom up in the sense that we will write our own implementation of these methods first. So we'll use basic pandas functions in order to implement these methods and then use the StatsModels functions. I think this is a nice way to make sure that you understand how these methods work, and then the libraries make them a lot easier to work with. And we've got some exercises to do as we go along. This is a 90-minute tutorial. I'm going to make sure that we wrap up right on time, but we'll have some things for you to do along the way. We'll look at two data sets. One of them is from the US EIA, the Energy Information Administration. We have monthly electricity generation from renewable sources from 2001 to the present. And the other data set that we'll use is surface temperatures, air surface temperature, collected by Our World in Data and available from 1950 to the present. And that's available for most countries in the world. So the analysis that I'll do is based on the US, but you'll have a chance to plug in whatever country you might be interested in. I have to admit, I have probably prepared more material than we will get through today. So my plan is we'll see how it goes. We'll get done what we get done. And if there's more left over, you will have the resources so you can finish it up on your own. And I can also make a video that will cover any material that we didn't get to. So rather than rush through things, I think we'll go at a good pace and just see how much of it we get done. The other place where you can find this material is Chapter 12 of Think Stats in the 3rd edition. I'm working on this now. It's in production with O'Reilly. The free version is available online, and there's a link there. So if you're following these slides, and you'll have access to these slides, you can use that link to get to the online version. And it is also now available to pre-order. So let's get into things. As I said, the first topic is seasonal decomposition. And the fundamental idea is that we're going to model a time series as the sum of a smooth long-term trend, some kind of seasonal variation, which is a repeating periodic pattern, and any other factor, anything that's not part of a long-term trend or a seasonal variation, we'll treat that as a random, unaccounted variation, an unaccounted kind of noise. As I mentioned, the first data set that we're going to work with is from the EIA, and this is all sources electricity generation in the United States. So we'll jump right in. Let's get to the first notebook. And again, the key to all of this is this URL. This will get you where you want to go. tinyurl.com/DOW24TS. And that's also in the resources tab on the AirMeet page. You have 2 choices for how you want to follow along with this tutorial. There are 2 notebooks, and I'll show you those links in just a second. There are 2 notebooks, one of them that does not contain the solutions, and it contains empty spaces that I've left where you can type along with what I do. So I'll demonstrate a method, and then you'll type it in your notebook as well. I think that's a really good way to learn. It'll keep you engaged. 90 minutes is a long time to maintain focus, and I think being active helps a lot with that. However, if that's not what you want to do, the other option is the notebook with the solutions in it that has all the code, and you can just execute it as we go along. So I will leave that up to you. And now I'm going to jump over following that link. Should take you to this page, which contains a little introduction for the tutorial. And then if you scroll down, links to all of the notebooks. So I'm going to click on this link here, which is the part 1 of this tutorial. And this is the notebook that does not yet have the solutions in it. And I'm going to type along as we go.
Hi, Alan. Could we possibly also just have the URL links? I believe it didn't get uploaded onto the resources tab. Maybe if you just type it into chat, I'll try to make sure that gets onto the URL of the resources tab.
Yes. I will put that in the chat.
Perfect.
Very good. And if that tiny URL doesn't work for any reason, this is the URL it goes to. This is alandowney.github.io, thinkstats, timeseries.html. All right. And let's get into that notebook. Make that a little bigger so we can all see it. So this is a Jupyter notebook running on Colab. If you're not familiar with the environment, the notebook contains both the text of the chapter and code cells. When you get to a code cell, you can either press the play button or more often hold down Shift and press Enter, and that will execute that cell. The first time you execute a cell in one of my notebooks, it'll give you a warning to let you know that Google did not write this notebook. I did, so you can run it anyway. And the first couple of cells are going to load a library that we need called empirical dist, and then download some support files. So if you hold down Shift and press Enter and run those first few cells, it should download everything you need and then import the libraries that we're going to use. This is a common set of libraries. We'll use NumPy, Pandas, and Matplotlib. And then ThinkStats is a library that's specifically for the ThinkStats book. We're actually not going to use very much out of that library. Mostly we'll work with Pandas and NumPy. The next section here downloads the data. There's some documentation there about where this comes from. And it's a CSV file that I downloaded, and it's in my repository, so you can download it from there. And if you execute this cell, it should download it. And then the next cell reads that CSV file and then does some rearranging of it. I think I won't get into the details of this. It's not super interesting. It is, in effect, taking that data set and putting it into a tidy format that's going to be easier for us to work with. We can see what the columns in that data set are. These are electricity generation from different sources in the US. And if you look at the index of that data frame, it contains the dates. So these are the months starting in January 2001 and going up to, I think, either August or September of this year. Now, here's where we get to one thing that I think is important for working with time series data. The index that we get from that CSV file, those are actually strings. So they look like dates, but they are really strings. And what that means is that Pandas doesn't really know that they are timestamps. And so we're going to replace that index with a date range. So this is a Pandas function called dateRange that's going to create a datetime index. And that index, as the name suggests, is aware that the values in it are datetime objects. And in particular, this date range has a frequency associated with it, which says not just that these are timestamps, but that they are known to be timestamps that are equally spaced in time and with a known frequency. And in this case, the frequency code ME means month end. So each of these timestamps will be the last day of the month that that data point is associated with. So you can see what the first few values look like. So instead of just saying January 2001, this indicates specifically the last day of January. Run that, and now the data is in the format that we want, and we're ready to get started with seasonal decomposition. And as I said, the fundamental idea of seasonal decomposition is that we can take a series like this. So this is electricity generation from nuclear power plants in the US. And we can decompose this into a smooth long-term trend, a seasonal pattern, and then random variation around that. And you can see here a clear seasonal pattern. It looks like there's an annual cycle in electricity usage. And that, if you think about the things that electricity is used for, it makes sense that there would be an annual cycle. Okay, so you'll see a number of cells in this data set that have this hashtag fill, and those are the places where we're going to do some work. So here's your first opportunity to get active. And what we're going to do here is compute a smooth long-term trend by using a moving average. And the idea of a moving average is to take noisy, highly variable data and smooth it out and find the long-term trend. And we're going to do that with a Pandas method that's called rolling. So I'm going to take that data set that we just loaded and run the rolling method. And we're going to give it a window that is 12 months. And the units here are 12 because this time series knows that the units are months. If you run this method rolling, what you get is a rolling object. And this is an object that has the ability to go through this time series and select from it windows that are 12 values long. And then we can apply a method to this rolling object that says what we want to do with each window. And in this case, we're going to compute the mean. So this is a moving average of 12-month windows. And if you run that, you'll get a new time series that contains 12-month averages. And notice that the first 12 values are NaN, not a number, meaning missing data. We don't get the first value until the 12th month in the series. So that's going to be our moving average, and that's what we're going to use as the smooth long-term trend. So I'm going to assign that to a variable named trend. And I'll just give you a second to get that line of code running, and then we'll move on. Okay. The next cell is going to just plot what we just computed. And we can see the original data in blue and that smooth trend in orange. And you can see it's maybe not as smooth as we might want it to be. We could come back to this and think about maybe using a longer window or using other smoothing methods. But just to keep it simple, that's what we're going to do for now. So there we have the first component of this seasonal decomposition, which is a moving average. The next step is to compute the detrended part of the signal, part of the time series. And we're going to do that just by subtracting off the long-term trend that we just computed. So we're going to compute the original series and subtract off the trend. When we do that, we're going to need to drop the NA values. So all the places where we're missing data, it'll drop those from the detrended sequence. And I'm going to assign that to detrended. Okay. And then we can plot that. So since we've subtracted off the part that was varying over time, the slow part of what was varying over time, what's left is pretty flat, pretty uniform over time. There's still some variation, but we hope that what's left is pretty close to just the seasonal variation and whatever remaining noise there is. So that's just the subtraction. We took the original series, subtracted off the trend, dropped the missing data, and that's where detrended comes from. Okay. To find the seasonal pattern now, we're going to group the data by month and then compute the monthly averages. And so that should give us a sense of what an average year looks like, what each month of an average year looks like. So if we take the index of detrended, oops, let's see if I can close that. We take the index of detrended. That's this series of date time objects. And we can ask each one what its month part is. And we can use that to group the values that are in this series. So we'll do detrended dot group by, and we'll group by the month numbers from 1 to 12. The result of that is a group by object. And if we now apply the mean method to it, what we get is the monthly average for the months 1 through 12, January through December. And we'll assign that to monthly averages. And the next cell plots that, and we can see what that looks like. Now, notice that the mean of this is near 0. That's because we subtracted off the long-term trends. So you can think of this as variation around the mean of the long-term trend. And each of these now is the monthly average. And you can see that there are 2 cycles per year. Electricity usage peaks in months 7 and 8, July and August, which are the summer months when people are using air conditioning. And then again in December and January, winter months, when they're using electricity for heat, among other things. Okay. So the seasonal averages that we have there are just for months 1 through 12. They don't line up with the data set. So to make the seasonal component, we need to repeat that monthly pattern several times. So we'll do that by taking those monthly averages and using the bracket operator to index into that series. And the indexes that we'll use are the original series dot index. We'll take the index part and take the month part. So each of these values will be a month from 1 to 12. We'll use that as an index into those monthly averages that we just computed. And what that should give us is a time series that now has repeated copies of those monthly averages that we just computed. And that's going to be the seasonal component of this decomposition. And if we plot that, it looks like repeated copies of those 12 values, not yet on the right index. And that's because I haven't given this an index yet. I need to set seasonal.index equal to the same index as the original time series that we started with. And now, if I plot that, that now looks like repetitions of the monthly averages over the same time series, over the same time stamps as the original series. So that's the seasonal component. And let me leave that code up on the screen just a little bit longer and give you a second to get that finished. Now, if we take that trend and add in the seasonal component that we just computed, what we get is a time series that is, in effect, the expected value at each point in the series. And so I'm going to call that expected. And if we plot that along with the original data set, so the expected value is the trend component plus the seasonal component. And we can see that there's pretty good agreement. I plotted these 2 lines with alpha so that they have a little bit of transparency, so that you can see where they overlap and where they don't overlap. And it's clear that these 2 components have captured a lot of what's going on in this signal, but not all of it. We can see places where the blue is a little higher than the predicted, or sometimes where the orange is a little bit lower than predicted. And so we can compute the leftover. The remainder is the actual series, and then we'll subtract off that expected sum that we just computed, and that's the residual. That's the third component, and it's the everything else component. And you can think of this as having 2 pieces of it. And one of them is exogenous factors, external factors that might be causing variation over time. And one clear example of that is things like weather. If we have an unusually hot summer or a cold winter, we would expect electricity usage to go up. And then other things like, equipment being added or removed from the system, things like that. So this residual is partly external factors like that, and partly just random things that happen in the world that we might not be able to observe or measure. So that's the residual piece. The next cell plots the distribution of those residuals, just to give us a sense of how the actual values vary around the predicted values. And we can see something that looks like a bell curve, and that suggests that these residuals are at least approximately like a Gaussian or a normal distribution. And that's fine, that'll be nice for statistical analysis. It's not really necessary. But in general, it's what we expect to see. If these residuals are the sum of a large number of random factors, when you add up a bunch of random factors, you often get things that look like Gaussian distributions. The last thing we'll do with this data set is to compute an R-squared value, which is a measure of how much we're able to reduce the variation if we take into account the trend and the seasonal pattern compared to the amount of variation in the original signal. So we can take the residuals and compute their variance. And we can take the original series and compute that variance. And they're both very big numbers, but the first one is substantially smaller than the second. And if we take that ratio, we can see that the remaining variation in the residuals is about 10% of the original. And to put that in terms of R-squared, we're going to subtract off that ratio, and that's what R2 is. So we'll display R2. And it's about 0.905. So this seasonal decomposition accounts for a large part of the variation in the data, which is a common pattern with time series. The R-squared values that we get are usually higher. If you collect data and look for correlations between things that are not varying in time, it is unusual to see correlations that are this high. With time series, we tend to see higher correlations. We'll talk about that a little bit later on. So let's jump out of the first notebook and back to the slides. And I want to recap what we've done so far and then introduce the next section. And we'll take a little bit of a break too, so you'll have a chance to catch up and ask questions. So what we did so far is to find the long-term trend by smoothing the data. We used a moving average to do that, and then we subtracted off that long-term trend. And then we found the seasonal component by grouping the data. In this case, we grouped by month, and then computed the monthly averages. And then we subtracted off that seasonal component. And then what's left is that residual component. You might also see the residual called an irregular component, and it includes those exogenous factors that I mentioned before, and also just things in the world that we think of as random. And then the decomposition includes also this cyclical component. In this case, we had a known period. We expected it to be a 12-month period, and so we treated that as a seasonal component. In other decompositions, you can also work with variations that might have an unknown period or a period that varies. Okay. So as I said, we'll take a break for about 2 minutes. I'll also take a look at the chat and see if there are questions. And when we come back, we're going to go back into that first notebook, and we're going to do the first exercise, which is to do the same seasonal decomposition using data from Our World in Data.
Perfect. Let me put some questions up to the screen. So the question is, when is it useful to apply center equals true for rolling mean?
Right. So it's really a question of alignment between the smoothed trend and the original data. And in this case, if you don't give it an argument, it aligns everything to the right. So the last data point in the series is the mean of the previous 12 months. So that you could think of that as a trailing average. The value at each point in time is the mean of the previous 12, as contrasted with centered, where it would be the mean of 6 months before and 6 months after. For this kind of time series analysis, I usually want it to be a trailing average because the goal is often to make a prediction for the future. And so we can think of this as like a snapshot at the present time. What's all the data that we know currently that we can use to make a prediction for the next time step? And so what I usually want is all of my data to be aligned at the last point of the time series, which is the present, or at least the point that we're making a prediction from.
Great. Another question. What are some other methods that can be used to find information about the trend instead of the moving average?
Sure. Couple of options there. One of them is there are different shapes that you might want for that window. So we used all 12 values and we gave the same weight to all 12 values. Often what you want might be something like an exponentially weighted moving average, where you give less weight to values that are farther in the past and more weight to values that are closer to the present. In signal processing, you often want windows that are a little bit smooth so that they don't have this weird effect of introducing artifacts into the time series. The other option for smoothing are things like LOS, which is a local regression method, which takes each window and does something like linear regression on the values in that window. So those are some of the methods for doing smoothing.
Brilliant. We have one last question, I think. If there is a trend, then you can use your techniques to capture it. But for global weirding, for exogenous events getting more unpredictable over time, how would we model that?
Yeah, really good question. You're exactly right. If your hypothesis is that things are getting hotter, the long-term trend would capture that. If your hypothesis is that it's becoming more variable over time, one of the ways to look at that would be the variance of the residuals, and to maybe take simplest thing would be to compare two intervals in time and see if the variance in the residuals is increasing. There are other things you could do to try to capture a gradual increase in variability, but that's where I would start. And you are anticipating the next data set, so this might be a point to jump back into it and start in on that exercise. Oh, okay. Sorry, before we get to the exercise, there was one more thing that I was meant to do here that I forgot, but let's come back for it. So that whole process that we just did, we did it by hand. We computed the moving average, we subtracted off the trend, we computed the seasonal component, we computed the residuals. You don't have to do this by hand. StatsModels provides a function that does it for you. Really, all we have to do is import the function and then run it. So we're going to do from StatsModels, we're going to import, and it is from StatsModels, we're going to go to TSA, which is time series analysis, and seasonal, and we're going to import. Let's see if it knows it. Yes, seasonal decompose. Now you notice that I did tab completion there. Colab does a pretty good job of looking into these modules and finding the names of the methods, which will both save you some typing and also avoid making errors. And so we're going to run seasonal decompose. And we're going to give it the nuclear time series. And the model that we're going to run is the additive model. In the next section, we're going to talk about the other model in there, which is the multiplicative model. And we need to tell it what the period is of the seasonal component. And in this case, we know that that's 1 year. And if you run the seasonal decompose method, you're going to get this object back. And that object contains all of the results. So I'm going to assign that to decomposition and run that. Now I'll give you a second to get that code working, and then when you do, you can run the next couple of cells, which will plot the results. And I'll do that. So this function puts all of the results into one big plot, has subplots. So here in blue, we can see the original series. This is the long-term trend. This is the seasonal component, and this is the residual. And you'll see that the results are pretty close to what we did by hand. Some of the details are just a little bit different in the way that this method is implemented in the library compared to how we did it, but it's pretty close. All right. Now we're ready for the exercise. And this is temperature data. This is air temperature 2 meters above the ground for most countries. And this is coming from Our World in Data. And just in the last couple of weeks, they've always been a great source of data, but just in the last couple of weeks, they have provided some APIs that are going to allow us to get at this data programmatically. And I've warned them that when we run this workshop, they might get a little bit more traffic than they're used to. But if you run the next two cells, what this cell does is it composes a request, and then it uses the requests module to send it to the Our World in Data site and gets back this response in JSON. And this is the metadata for the data set that we're going to use. So I'm going to run this cell. And then I'm using pprint, pretty print, to display the results. And this is all of the metadata associated with this data set, where it's from, a little bit about how they did the processing, and the units of the measurements, and lots of useful details here. I've worked with so many data sets that do not have this kind of metadata. It's a really welcome change to see how well documented this is. The next cell actually downloads the data. And again, it's composing a query and then using requests to send that query. And you'll notice here that there's a country code where I put in USA. So if you want to follow along with the same data set I'm using, you can leave that unchanged. But if there's another country that you're interested in and you know what its ISO 3-letter code is, you can put that in there. If you don't know the ISO codes, you can use that link. So I'll construct that query and then send the request and display the first few lines of that data set. If that doesn't work for any reason, there's a backup here. You can uncomment these lines of code and it will download the same data from my repository. But again, I think the Our World in Data is such a great resource. I wanted to make you aware of it and show you some of the ways to access it. Now, there are two columns here that we're going to work with. One of them is temperature 2 meters. Again, this is measured 2 meters above the surface. The second column actually has the same name, and so it gets this suffix to distinguish it, and it is the annual averages. So we're going to ignore the second column. We're just going to use the first column. And we'll select that out. So that's going to be, we'll get the temp series, and that's going to be our temperature data frame, and we're going to select the temperature 2 meter column. And if you look at that temp series, currently the index is just the numbers, 0 up to the end of the series. So we're going to give that temp series an index where we pull out temp df, and we're going to pull out the day column. So now we've got timestamps in there. And if we plot that, we now have, starting in 1941 up to the present, surface temperature averaged over the United States. And clearly there's a seasonal component, and we're going to do the decomposition in order to compute the long-term trend, the seasonal component, and the residuals. So I'll give you a minute or two to get started on that exercise, and then I'll get started as well in order to walk through those steps. If you're making progress on the exercise, you can feel free to ignore me. But if you would like some help getting started, I've started to fill in the pieces here. So we're going to want to run seasonal decompose. We'll give it that temperature series that we just selected. The model we'll use is the additive model. And again, the period is 12, because this is monthly data. And again, we're going to get that decompose object as a result. So we'll assign that to a variable, and that will allow us to run plot decompose. And let's see what that looks like. And what did I leave out there? All right. It needs to have the original series as well as the decomposition. That's taking a little bit longer than I expected. There we go. So there's the original time series. It took a long time because it was trying to plot all of those values on the x-axis. Here's the long-term trend, and it sure looks like average annual temperatures in the US have increased over the last 70 years. The seasonal component and the residuals. And again, to compute an R-squared value, we'll compute 1 minus the variance of the residuals compared to the variance of the original series. And that value is something has gone wrong. So this resid refers to the previous thing I computed. I need to pull out the decomposition. I need to pull out the residual part of that decomposition that I just computed. And now we can see that the R-squared value is about 0.99. Okay, so that's where we'll stop in the first notebook. You'll see that there's an additional section there that's about prediction. We're going to do prediction in the next section when we talk about the multiplicative model, which is part 2. So let's get into that. And this is motivated by the observation that in the additive model, as the name suggests, we assume that the long-term trend, the seasonal component, and the residuals add up. But we could also think of a scenario where the seasonal component might be proportional to the current values. And the example that we're going to look at in a minute is solar power. And this is probably a perfect example where the more solar panels you have deployed, if you have variation over the season in the amount of sunlight that hits those panels, the magnitude of that variation is going to depend very directly on how many panels you have out there. And similarly, if there's any random variation, an unusually cloudy month or something like that, it's going to affect many of the panels, and so the effect would be proportional. And so if we have proportional effects like that, then we would expect the seasonal variation and the residual to be multipliers of the long-term trend rather than additive components. So to see if that's true, let's get into the second notebook and we'll look at how electricity from solar panels has varied over time. And to do that, we'll go back to this page. And again, you have your choice of running the notebook that has the solutions in it already, or running the one that has the fill-in places. And I'm going to do the one that has the fill-in places, no solutions. All right. When you open this notebook, you want to hold down Shift and press Enter a few times. We're going to run the same code from the previous notebook that does some setup, and then some of that code copied over from the previous notebook to do the same things that we saw there. And when you get to this cell, it should load electricity generation from small-scale solar photovoltaic sources plotted over time. Then I'll just take a minute for all of that to run. And we can see what that looks like. So a clear increasing trend since this data set started in 2014. The deployment of solar power has increased, and it seems to be accelerating. But also the magnitude of the variation is increasing, which is consistent with what we thought might be the case. So that's a good indication that the multiplicative model might be a good choice here. And so we'll see what that looks like in just a second. Now, I promised that we were going to do prediction, and here's the point where we're going to get to that. Before I start generating predictions, I'm going to split this data set into a training set and a test set, and I'm going to do that by selecting the last 5 years of data and see if we can use the previous data to make those predictions. So I'm going to run this function that's called split series. And the definition of that function is, that's one of the functions that you defined earlier in the notebook. And that's going to return two time series, which I'm going to call training and test. So what we're going to do is make a decomposition using the training data, and then we'll generate predictions, and then we'll compare them to the actual values in the test data set. So again, I need to import from StatsModels.tsa.seasonal. I'm going to import seasonal decompose. And it is, right, seasonal decompose. And run seasonal decompose with that training data. The model now is going to be the multiplicative model. And the period, again, will be 12 months. Get that decompose object and assign it to decomposition. And again, we can plot those results. So in the training data, we have data that goes up to about 2019, the endpoint of 2019. Here's that long-term trend. Here's the seasonal component. Notice that the seasonal component is now multiplicative. So the mean is 1, and the peak is about 25% higher, and the trough is about 25% lower. And the residuals are also multiplicative. So the peak here is apparently off by about 5%, or maybe 6 or 7% during one particularly bad month. And then after that, closer to 1, usually maybe 2% high or 2% low. From the decomposition object, we can extract the trend, seasonal, and residual components and compute the R-squared value. And notice here that it's really, really high. And again, these are time series. R-squared values are often substantially higher than what we see in other kinds of data sets. All right, so now we need to generate predictions. And we're going to do that by applying a linear regression model to the long-term trend. I'm not going to take a lot of time on this. If you are familiar with the StatsModels function called OLS that does ordinary least squares, you might recognize that this is a formula using PATSI. This is a language for specifying a regression model. And it says that the long-term trend is going to be a function of two explanatory variables. And one of them is just the number of months since the beginning of the time series. And then this is the PATSI code for adding a quadratic term. And that term means months squared. So this model fits a parabola to the long-term trend. And we can see what the results look like. We get estimated coefficients for the intercept, months, and months squared. The p-values are all really small because, as we're going to see, this model fits the data pretty well. And so now we're going to use this model to generate a prediction. The results, this results object, has a predict method, and it requires a data frame that has in it the months that we want to use to generate those predictions. So give me just a second to find my notes and we'll fill in that code. Right. Okay. So we need to run results.predict and we need to give it a data frame. So we need to construct a data frame that has the months from the original data. So we'll compute months, and that's going to be a range of values that goes from 0 to the length of the original data set that we started with. And we need to put that array into a pandas data frame. And we'll put that into a dictionary that contains a column called months, and it contains that data that we just computed in the column. And we'll pass that data frame off to the predict method. And this now takes that long-term trend and generates predictions both for the past, so retrodictions based on the previous data and also going out into the future. And I'm going to assign that to the predicted trend. Now notice that the index is 0 up to the total number of months. So I'm going to replace that. I'm going to give this series a new index. And it's going to be the same index from the original series. Okay. So again, what I did there is to create a data frame that has the months where I want to generate predictions. I used the results from the linear regression to generate predictions for those months. And then I created a time series that has the same index as the original data set, so I can plot it on the same axes as the original data. And here's what that looks like. It's a quadratic model, so it fits a parabola to the data, which means that it captures both the increase and the acceleration over time. And we can see that in the past, in the retrodictions, the model fits the data really well, and that's what we saw with that really high R-squared value. And going out into the future, we can see that the prediction that we would have made in 2019 is that solar power would continue to increase and continue to accelerate. So we have a prediction now for what we think the past trend is going to look like. What we need to do now is add in the seasonal component. So I'm going to compute monthly averages. And we'll do that in the same way that we did in the previous lesson, which is to take that seasonal component, and we got this from the decomposition computed by StatsModels. We'll take that seasonal component and group by month. So we'll group by seasonal.index.month and then compute monthly means. So I've got monthly averages now, and I can add them in to the predicted trend. So the predicted seasonal component is going to be those monthly averages. And I'm going to use as an index into that array the months from pred trend. And let's see what that looks like. Pred seasonal. So now I've got a time series that contains monthly averages, and I need to give it the same index as the pred trend. And that will allow me to add, I said add, but remember this is the multiplicative model. That will allow me to now multiply the trend, the predicted trend, and I'm going to multiply that by the predicted seasonal component. Let me do that multiplication and make sure that it works. And now the product of those things is the prediction that I'm going to make. Now in a minute, I'll run the next cell. It's going to plot the results. But before I do that, let me give you a minute to catch up because that was a lot of code. All right, let's see what it looks like. Okay. The blue line here is the training data, and the gray line is the predictions, both for the past, the retrodictions, and now the predictions going out into the future. And we can see again that the model fits the past data very well and produces predictions that at least seem reasonable. It captures both a long-term trend that is increasing and accelerating and seasonal variation. And if we run the next cell, we can now see how well those predictions actually do. This is now just the prediction part. So starting in late 2019 up to nearly the present, the blue line, again, is the actual data, and the gray line are the predicted values based on only the training data. For the first few years, they're quite good. And then it looks like reality accelerates a little bit faster than the model predicted. And that's actually been a consistent pattern with solar power over the last several years. Every time we make predictions, it turns out that actual growth has exceeded those predictions. So again, let's take a break for a couple of minutes. If you want to get up and stretch out a little bit, please do that. And we'll come back and get into part 3. I can also take any questions that have come up during that segment.
I think you have been very comprehensive because I don't think there has been any questions.
No new questions. Okay. Well, let's take a break. We'll come back in 2 minutes, which will be 5 past the hour.
Oh, sorry. Literally freshly coming in. There's a question.
Right. Very good.
For trends in sales, supply, and demand, do we expect additive or multiplicative trends?
That's a great question for sales. I could make an argument for either one. And that might be a case where you need to do some exploration of the data and see which model fits better. Maybe run both models, look at things like R-squared as a way of measuring goodness of fit and see which one works better. Because again, I could think of different scenarios where it could be additive or multiplicative.
Cool. Thank you, Alan. Oh, look. Once people know that you're taking questions, the questions are all pouring in.
Very good.
The documentation for spectral analysis and signal processing methods for denoising time series.
Good question. Yeah, there's really interesting overlap between time series analysis and signal processing. A lot of the methods are the same. Sometimes you see somewhat different vocabulary in the different domains. I think just learning about signal processing is a really good idea. If you are a data scientist and working with time series data, I think it's just good to know about signal processing. I do have one recommendation, which is I have a book that's called Think DSP, which is about signal processing. And there is a little bit in there about smoothing and spectral methods. So take a look there.
Perfect. There is I think more of a question to everybody else in the chat. Oh, actually, sorry, that was this question, which is, has anybody looked into which country has more predictable or less predictable temperatures?
Yeah, I'd love to hear if people ran other countries, what did those results look like compared to what I saw?
Brilliant. Let's do one last question. Does StatsModels have a good support for multiple time series like a panel?
Yeah, good question. Honestly, I haven't worked with that part of the library. I really don't know. I just have to send you to the documentation.
Thank you again, Ellen.
Good. All right, let's get back into it. Let me wrap up some of the topics from part 2, and we'll get into part 3. So the motivation again here is that sometimes that seasonal component is going to be proportional to the current value, and solar power is a perfect example. Often those residuals are also going to be proportional to the current value, and in those cases, that multiplicative model is going to make more sense. The other thing we saw in part 2 is prediction and validation, and we did that by splitting the time series into a training and a test series. And I'll just mention as an aside, this is a common pattern in machine learning, and often when you split data, you'll split randomly. So you'll take your data set and do a random selection of one third for testing and 2/3 for training or something like that. With time series, what you most often want to do is simulate a prediction scenario. And what that usually means is that there's a point in time where you have all the data from the past and none of the data from the future. So this is a case where prediction really means prediction. You are predicting things about the future. And again, we use the training data to fit the model and generate the predictions, and then the test data to do the evaluation. This is the apparent Danish source of the commonly known phrase, it is difficult to make predictions, especially about the future. And that is one of the things that we saw in that example of solar power is that the model fit the past data extremely well, and it made pretty good predictions over the short term. But then eventually just things happen in the world that the model could not have predicted. So I suggest often using the word projection rather than prediction to describe what this kind of modeling really does, because a projection says, in effect, if current trends continue into the future, here's what would happen, with that stipulation that nothing comes along and causes major large-scale changes. And that's as contrasted with a prediction. If you say, here is what I think will happen in the future, you are effectively saying, I don't think anything will come along with large-scale changes, and with real prediction, there just always are.
If you're sharing a screen, by the way, nothing has been shared yet.
Good. Thank you for the reminder. When I switch back and forth, it's easy to forget. Okay. So I won't say all of these things again, but just to show you the slides that you didn't see before. Here are the key ideas from the second part. A little commentary on doing training and test with time series data. And then here's that Danish expression that I mentioned. Okay. There's an exercise in the notebook where you have a chance to take that same method that we just did with small scale solar generation and apply it to utility scale. I think let's not do that as part of the tutorial. There's nothing new in that section. It is applying the same methods. So let's get into part 3. And this is introducing another way of doing both the analysis of a time series and prediction. And this is ARIMA. So we'll jump in, and this is actually notebook 3 that we're going to go to. So this slide is incorrect, but we're going to jump into notebook 3. And again, we'll follow this pattern where we will first do it by hand, and then we will use StatsModels. And in the interest of time, I am going to jump into the version here that does have the solutions in it. So we'll do a somewhat faster run through of this part of the code in order to make sure that we're finishing on time and that you get to see ARIMA analysis, because I think it's a great topic. So again, in the third notebook, run those first few cells. It will load up our libraries. It will load the data from the previous notebook and some of the functions from the previous notebook. And when you get to here, it will compute year-over-year differences in that original time series, the nuclear data that we started with. So I'll give you a section to get that notebook loaded and run, and then we'll see what this data set looks like. Okay. So again, this is electricity from nuclear power over time. And these are the year-over-year differences. The reason for computing these is the first idea of ARIMA analysis is that often it is easier to predict the changes than the actual values. And sometimes those changes are the immediate difference between each value and its successor. And sometimes it's things like this where we have, again, reason to believe that there are seasonal patterns here. So computing a year-over-year difference is a way of computing like this July compared to last July, and then this August compared to last August. And again, this is one of the fundamental ideas of ARIMA, is that sometimes the differences are easier to predict than the original values in the series. The way we're going to make these predictions is by computing serial correlations, and also called autocorrelations. And this is the correlation between each value in the series and its predecessors in the series. And in this case, I'm going to compute 3 lags. So a lag is a copy of the time series that is shifted over by some number of cycles. And in this some number of periods, and in this case, the period is 1 month. So I'm making here a new data frame. So I'm creating a new pandas data frame, and I'm going to loop through 3 lags in order to compute 3 shifted copies of the original data. So I'm going to take those differences and shift them by 1, 2, and 3, and add them to a data frame. And then let's see what that data frame looks like. So here, in the first column, these are the original values, the original differences. And this one is lagged by 1 time step. So we can see that value here, 2434, appears here shifted by 1. It appears here shifted by 2, and here shifted by 3. So the data frame has 4 columns, the original and 3 lagged copies. And if we now compute the correlations, we can see that there are strong to moderate correlations between the time series of differences. The previous value, the correlation is about 0.56. The time from 2 months ago is about 0.29, and 3 months ago is about 0.22. So this time series, like most time series, has these serial correlations, or more generally, autocorrelations, and we can use them to make predictions. And we'll do that again by using StatsModels, the OLS function. We're going to run a linear regression that tries to predict each difference by using the differences from the previous 3 months. And here's what that looks like. Again, we're importing the OLS function, and we're running it this formula. Let me show what that formula looks like. the formula says that this month's difference is going to be a linear function of the previous three lagged values. And if we display what those results look like, here are the coefficients. And if we look at the p-values, we can get a sense of how much information these lagged values are providing. It's clear that that first correlation is pretty strong. The second and third are, from the point of view of hypothesis testing, borderline. And then the R-squared value gives us a sense of how predictable these differences are. Now, this is a lot lower than the R-squared values we were seeing before, and that's because we're not predicting the values anymore, we're predicting the differences. So that's the model that we have so far. And now we can compare the predictions to the actual values by using this predict method. So this is the results from that linear model that we just ran. We're running the predict method. And now we can compare the predicted values to the actual values. And we can see that it tracks reasonably well. There's pretty good overlap between the blue actual differences and the orange predictions. You might see that it looks like the orange one is shifted just a little bit to the right. And what that means is that it tends to lag behind just a little bit. That when the blue line increases or decreases abruptly, it takes a couple of time steps before the orange line catches up with it. And that's partly the motivation for the next section. So we can take those results we just computed and compute the R-squared value, and it's okay, but not great, and we'll see that there's some room for improvement. And that's the motivation for the next part, which is the moving average part. And it's a way of taking that same idea that we just used, which is when we look at these differences, we see that there is autocorrelation, which means that the past predicts the future. But we can also see that it's not perfect. There are errors. So when we compute the residuals, there are consistent patterns in the residuals as well. So we're now going to do exactly the same thing that we just did with the residuals. Sorry, the same thing we did with the differences, except that we're going to do it with the residuals. So I'm going to make another data frame that contains shifted copies of the residuals from the previous step. Now, in this case, instead of doing 1, 2, and 3, I'm going to do 1 and 6. And that's because I poked around with this data a little bit, and these are some lags that I found that worked reasonably well. This is one of the things that you'll do with an ARIMA model is try different versions of the model, different lags to see what is effective. So again, I'm going to create a data frame that contains shifted copies of the residuals, and I'll use OLS again to compute the correlations between them. Now, in this case, the R-squared of this model is not great. It is only about 2%. And what that's saying is that for this particular data set, the moving average part of the model is not computing a huge amount. It's not contributing a lot of predictive value. Nevertheless, we'll continue just to show how the method works. In the same way, we're going to use the results from the moving average part of the model, generate predictions. And we can think of these now as being a corrective on the predictions from the AR step, from the auto-regression step. So we're going to take the predictions from AR, and we're going to add in these corrections from MA, and that will be the total predictions. And now we can see that those R-squared values have increased just a little bit. So in this case, the MA part of the model didn't It helped a little bit, but not a ton. Let me say one quick thing about the vocabulary here. The moving average part of the model has kind of a weird name. What we actually did was to apply autoregression to the errors from the first stage. So I really think of this as being autoregression stage 1 and then autoregression stage 2. Stage 2 is called moving average because it has the effect of smoothing the data in a way that is analogous to a moving average way of smoothing, but I think it's an odd piece of vocabulary. I don't find it very helpful. Okay. The next step here is to take that model that we just built and use it to generate retrodictions. So that is to say, we're going to try to fit the past data. There are some details here that are just a little bit annoying because when you shift these data sets around, you get a lot of missing data at the beginning and the end. And when you compute the autoregression model, you also have some places where you can't fill in all of the data. So in the notebook here, you're going to see this n missing and some additional code that's there primarily to handle all of those details. But this is the key step, and this is how we get from predicted differences to actually the predicted values. And we're going to loop through the time series, and at each point in time, we're going to compute the ith element of the series. And we're going to use it by looking back in time to the I-12 point in the series. And then we're going to add in the predicted differences. This chunk of code here is the key to understanding the I part of ARIMA, which is the integration part, because this is analogous to what you would see in a numerical method for doing integration, like calculus type integration, by taking previous values and adding in differences which are analogous to derivatives. So this is how we get from the predicted differences to the actual predictive values. Let me run these cells, and then we can see what that looks like. And it looks pretty good. The orange, again, is the predicted values. The blue is the actual values. And the model does a pretty good job of capturing both the seasonal variation and some of the random variations in time. And the residuals, the R-squared value comes out to about 0.85, which is a little bit better than what we got from the seasonal decomposition model. So that's ARIMA, and I should now explain where all of the pieces of this name come from. The AR part of ARIMA is the autoregressive step, and that's that first linear model that we did. The MA is moving average, and that's the second autoregression model. And the I is integrated, and that refers to that last step that we just did that looks like a numerical method for doing integration. The last piece of this is that S, which is the seasonal part. And that's because in this case, when we computed those differences, we computed them across a 12-month period rather than a 1-month period. So that was the seasonal part. So to summarize, the big idea in an ARIMA model is first that instead of predicting the values themselves, we predict differences. The second belief is that the future will be like the past, and that's what motivates the autoregressive part of the model. And the third piece is that errors in the future will be like errors in the past. So that's why we can use that second model to try to correct those errors. And then the integration part is kind of a funny use of integration, but it refers to the way that we now get back from predicting changes to predicting the actual values. So that's ARIMA. And again, if you add in the seasonal component, it's called SARIMA. There's also the option of adding exogenous variables. So for example, if you have temperature data and that changes electricity consumption, you could add that as an external or exogenous variable, and that would be SARIMAX. One note about that, though, is be careful about adding exogenous factors to a predictive model, because if you can't predict the weather, then it's not useful to put weather into a predictive model. I talked about this a little bit, how the names are a little bit misleading. I won't belabor that point. But the last thing I'll mention is that you don't have to do ARIMA from scratch, as we just did in this notebook. It's built into StatsModels, and the notebook will show you how to now to take the model that we just built and express that in terms of the order, which has these parameters P, D, and Q, and also in terms of the seasonal order, which has capital P, D, Q, and S. I won't get into that right now. There's an exercise in the notebook that you can do that takes that same model that we just did with nuclear power and applies it to hydroelectric power. So give that a try. It'll give you a chance to practice with these methods and also to use the StatsModels library rather than doing it by hand. So I'll wrap this up. We are just about out of time to say time series analysis is kind of special because we have these specialized methods that take advantage of seasonality and autocorrelation. We did two versions of this. Seasonal decomposition is the simpler version. We did two versions of it, additive and multiplicative. And then ARIMA is a more versatile model. It's a little bit more complicated, but honestly, if you're using a library like StatsModels, it's not more difficult. It's just a richer model. I talked about this a little bit about how when you are working with time series data, you often see R-squared values that are higher than you expect to see in other places. And then I will wrap this up by giving you some resources that you can come to in the future. One of them is the documentation of StatsModels, which is very good, and their time series library. In particular, I would point you to STL, going one step beyond seasonal decomposition. This is a useful tool. And then lastly, this all comes from Chapter 12 of Think Stats, and that's available online now. And if you are just getting started with Python, you might also find this book, Elements of Data Science, useful. And lastly, here are some ways to get in touch with me if you have questions. I'm sorry I didn't leave more time for questions now, but we might have a chance to do just one or two. And I think we have literally a minute. So is there maybe one question that we could do, or maybe we should stop there?
Thank you again, Ellen. I think timing-wise, it might be a little bit tight to do
Yes.
the last question. And I think you have answered many, many questions already throughout the tutorial today. So thank you again for a great tutorial. Just some housekeeping notes. The replay will be available just on the very same link, and the resources should also be available in the right-hand side of the panel. And do join our PyData global Discord, where if you have any more questions, do feel free to ask, and we will try to monitor that. Thank you again, everyone, and goodbye, and see you at the next session.